Right, as you know, because you've had lots of time to read the great title slide here, we're going to be hearing about extending the C and C++ memory model with inline assembly, and of course, Paulo is giving the talk.
Yeah, thank you very much for the introduction. So this is joint work with Lahav, Viktor, Vafeiadis, and Azalea Raad. So I would like to start with a brief overview of the talk by explaining what's the problem we try to solve, what's the motivation for tackling this problem, and what are the challenges. So simply put, the problem is to devise semantics of concurrent programs with inline assembly. And the motivation is that inline assembly is a very powerful tool of C++, but unfortunately it is under-specified. So for those who don't know, inline assembly allows one to insert snippets of x86 assembly directly into C++ code. And there are many applications, many reasons why one would like to do so. One of them is to write efficient code directly in assembly. A second one is to have access to instructions that are not in C++. And a third application is to customize the call convention of naked functions. So to give a concrete example of this second application, I have here a program that uses inline assembly to have access to non-temporal stores. So a non-temporal store, simply in simple words, is a store that bypasses the cache. We are going to revisit this instruction on the talk. And we are going also to use inline assembly blocks under a much simpler syntax. So I'm going to refrain myself from explaining the details of this block. All that we need to know to understand this example is that this non-temporal store is going to move the value 42 to the variable destination. So by the end of the execution of this inline assembly block, the variable destination will store the value 42. So the challenge of devising semantics for concurrent programs with inline assembly is that the architecture, x86, and the source language have incompatible concurrency models. So in the first part of the talk, I'm going to elaborate more on what are these incompatibilities. And in the second part of the talk, I'm going to explain our extended concurrency model for C++ with inline assembly. To appreciate these incompatibilities, it's good to have a basic understanding of the concurrency models of C++ and x86. So I prepared this short slide where I introduce RC11, the model for C++, and EX86, the model for x86 assembly. So in C++, to access memory, we have to specify a mode, an access mode. And there are basically two classes of access modes. There are atomic access modes and non-atomic access mode. So atomic access modes are used to establish synchronization, whereas a non-atomic mode can only be used once you establish synchronization. And I'm going to use this example to explain access modes. And it's good to understand this example because we are going to revisit this example very often throughout the whole talk. And we have here two threads, one that performs two writes to the variable x and to the variable y, and another thread that performs two reads in the inverse order. And here we can think of y as a flag that tells whether the variable x has been updated. So if the thread T1 reads 1 from y, we would expect that it reads 1 from x. So this is the case if we used the SC mode, which is the strongest one in terms of synchronization guarantees. But it is not the case if we use the weakest mode in terms of synchronization guarantees. And what is key in C++ is that we have a mode in between, relax and SC, that allows you to restore synchronization. Now moving to x86, to the model of x86 assembly, there are basically two properties that are important for this talk. One, that by default x86 disallows this weak behavior where we read 1 and 0. And a second property is that using non-temporal stores, the weak behavior is allowed. And the reason is that a non-temporal store, again, is a store that bypasses the cache. So it could be the case that X goes to T0's local buffer, and Y goes directly to memory. So T1 would read the value 1 from Y in memory, but would not read the update to X. So having understand this, we can already appreciate the first incompatibility between the C++ memory model and x86 memory model. And we can see that a non-temporal store breaks release-acquire synchronization. So a release write in when the target of compilation is x86 is compiled to a plain write. So as we saw before, a non-temporal store can be reordered with a plain write. So in this case, it could be the case that X and Y are reordered, and we would see the weak behavior. So the challenge is to relax the model of C++ in such a way that this behavior is allowed. And we also want to suggest new ways to restore synchronization in the presence of non-temporal stores. A second incompatibility is due to compiler optimizations. So here we have basically the same example as before, but instead of a non-temporal write, we have just a plain store. And the compilation to this, of this program is to plain access modes in x86. And as we saw, this behavior is disallowed. So this could suggest that we wish to enforce the same constraints, the same consistency constraints of x86 to the source code, but that would be unsound because of compiler optimizations. So RC11 allows the mode, the relaxed mode to be, relaxed reads to be reordered. So if the compiler performs this optimization, then we could witness the weak behavior. So the challenge here is that x86 consistency breaks some of the compiler optimizations. A third challenge is that we cannot model inline assembly access using the standard, the existing RC11 access modes. So we cannot use SC because it's stronger than inline assembly access, because the compilation inserts strong memory fences. And we cannot use the other mode of access because they are weaker than inline assembly, which is not optimized like the other ones. So the challenge here is to devise new modes to describe inline assembly accesses and discover how they relate to the existing ones in RC11. So now moving to the presentation of our solution, our extended model, I'm going to explain how we solve each one of these challenges. So the idea to solve the challenge of non-temporal stores breaking release acquire synchronization is not to remove the synchronization edges between release and acquire access, but actually to remove the synchronization access within a thread. So in RC11, every local access is by default synchronized. But now in our extended model, we remove these synchronization edges when it's a non-temporal store. However, we do allow the synchronization edges between non-temporal stores and store fences, which is an instruction from x86 that's meant precisely to stop the reordering of non-temporal stores. And by transitivity, we would get the synchronization between the write to X and the read to Y. So the second idea to solve the problem with compiler optimizations is to enforce x86 consistency only on threads that include inline assembly blocks. So that's actually a great simplification of how we actually formalize this idea, but is a first simplification to understand. So here, this weak behavior would be disallowed, but because of compiler optimizations, x86 would not apply to consistency, would not apply to this thread, which could witness the weak behavior. And third, to tackle the problem of access modes not handling inline assembly access, we introduce 3 new access modes: TSO for plain read and writes, a mode for non-temporal stores, and a mode for store fences. So what's striking about this ordering is that we don't have a total order anymore on the guarantees of synchronization. And we also, it's weird that we don't have any relation between non-atomic access and non-temporal stores. And it's also a bit striking that we don't have TSO as weaker than SC. So to explain why we don't have these orderings, I'm going to show examples where we have each one of these modes weaker than the other. So here's an example where non-temporal stores can be weaker than non-atomic access. And the example is basically just the same as before, because non-temporal stores break the release-acquire synchronization, whereas non-atomic access don't. And also the converse is true. Non-atomic access can be weaker than non-temporal stores because racy non-atomic access leads to undefined behavior, whereas in our model, racy access to non-temporal stores do not lead to undefined behavior. So this begs the question why we made this choice. And there are many reasons, and here we cite only 2. One is that one of our design goals is to have programs fully written in inline assembly have x86 semantics. But if we made racy access to inline assembly UB, then we would not be able to have this property. And a second reason is just that inline assembly is not optimized as non-atomic access. So we don't need to introduce UB to justify some of the soundness of these optimizations, like in non-atomic access. So finally, why TSO is not weaker than SC? So here's an example where SC is weaker than TSO. And the reason is that in RC11, SC access, when you mix different modes of access to the same variable, then it might be the case that the semantics is weaker than SC. So this is an example where we have this weak behavior allowed, even though we use SC. We do not have the weak behavior on the thread that use inline assembly, because as I explained, threads that use inline assembly abide by x86. We also have some properties of this model. So we have the property that programs fully written in C++ have unchanged semantics with respect to RC11. We also have the property that programs fully written in inline assembly have x86 semantics. And we have a data race freedom theorem, which means that programs with data races only on SC axis have SC semantics. Finally, we proved the correctness of compilation and of many compiler optimizations with the notable exception of one compiler optimization called sequentialization. Sequentialization merges 2 threads into one by interleaving their instructions. And the reason why this is not sound in our model is because it is not sound in x86. And the reason why it's not sound in x86 is that there's a difference in x86 between reads, internal reads and external reads. External reads enforce synchronization, whereas internal reads don't. So if you sequentialize, you turn an external read into internal read, and you lose synchronization. So to conclude, I justified why inline assembly is an important tool, and I explained that in this talk we wish to provide semantics for concurrent programs with inline assembly. I explained some of the challenges in coming up with such a model. One is that non-temporal stores break release-acquire synchronization. A second one is that x86 is compatible with many of the compiler optimizations. And a third reason is that inline assembly access cannot be modeled via RC11 existing access modes. I explain how our extended model tackles these challenges. So in particular, I explain how to restore release acquired synchronization using store fences. The idea that x86 consistency only is limited to the scope of threads with inline assembly. And I explain the new access modes to model inline assembly access. And I also explained some of the properties of our model, namely that it extends RC11 and x86. It satisfies a data race freedom property, and it proves many of the compilation schemes correct and compiler optimization as well. Thank you very much. I'll be glad to take questions.
Questions, go ahead.
Hey, nice work. I'm glad someone's done this. It's been a long time coming. A couple of questions. I'll ask you one offline because it's probably a longer one. First two, compilers, obviously they support all of the architectures that they generate, right? So you can have inline assembly for ARM,
yes.
IBM, MIPS, x86, RISC-V, so on. Have you thought of like automating this so you can come up with a family of models for each architecture the compiler will target? Because super handy to be able to reason about all of these different architectures. But also, how would this sort of manual approach of mushing these models together deal with changing architecture models? Because they have changed over the years, right? That's two questions.
Yeah, so unfortunately, our solution is tailored to x86. And it gives some ideas of how to come up with a general way of combining models. But as it stands now, it's tailored for x86. And I have ideas of how to extend this work to ARM. But due to many incompatibilities between these two architectures, it's difficult to think about a general way of combining them.
Yeah. I mean, that's my third question. So RC11 forbids load buffering, but you can observe it on ARM. So that's kind of an incompatible set of arrows, right? So we can talk about that later. But nice work. Thank you.
Thank you very much.
Thank you very much for the talk. So my question is, suppose you have an atomic read in one thread and inline assembly read in another thread, and these two operations are not sequenced. Is that allowed under this model?
What is allowed?
So like two racing reads, one atomic, one from inline assembly. Is that like something that your model permits?
Yes.
Okay, because I had a debate on the C++ mailing list about this because they said that you cannot, they believe in typed memory, basically. You cannot have an atomic operation and a non-atomic operation on the same like memory location, which obviously you can do that through inline assembly. Yes.
I mean, on our toy formalism, that is perfectly fine. In actual C++ code, you would have to do some casting to change the type from atomic to just the type of a variable, an integer variable. But our model is handles gives semantics to programs that mix these accesses.
Okay, thank you.
Hi, cool talk. Does your model support operations that work on more than just an integer? So these streaming operations are used to move data fast, and like if your CPU has AVX, it's going to try to move like 512 bytes at a time.
Yeah, thank you for a question. No, it doesn't support. Our model is limited to integers.
Okay.
Yeah.
Okay.
I mean, the generalization to other basic types is straightforward, but to more complicated instructions, as you mentioned, it's not straightforward.
glibc uses that a lot to move data fast. So I wonder if you could find like miscompilations where the program doesn't match what the developer wanted, if you call like memcopy or something like that. I know they're not atomic, but different threads might try to do it, so no.
Yeah, that's definitely an interesting idea for future work. Thank you very much.
Thank you.
Okay, we're right at time, so let's thank Paulo again. Thank you.
Thank you.